In this video, we'll take a look at some common indefinite integrals. Indefinite integrals just being a different word for antiderivatives. All of the information in this video can be found on page 332 in the textbook. It's a lot of information, it's a lot of good information, and it's a lot of information that we could figure out based on what we know about derivatives. So the first thing we need to talk about here is just what the indefinite integral is. Here is a definition for an indefinite integral, and it basically says that if the derivative of f of x is f prime of x, then the indefinite integral, and we use the same symbol as we use for the definite integral to find the area, the indefinite integral of that derivative is going to be the function itself plus some constant of integration. This constant of integration is really important because when we take the derivative of this expression here, the derivative of f of x is going to be f prime of x, as was stated in the hypothesis of this definition. But also, when we take the derivative of c, that's going to be 0. So if we take the derivative of any function, f of x plus any constant, then we're going to get f prime of x. So there are a lot, in fact, infinitely many functions that have a derivative of f prime of x. The antiderivative gives us all of them, and we need to include this constant of integration so that we can include all of those. So a few properties about indefinite integrals. The first is a property of definite integrals also. If we take the integral of a constant times a function, that's the same thing as the constant times the integral of the function. And this is true for all k values in the real number. So any constant k that's a real number. This definition right here, or this property, is also a property of definite integrals that we've seen, the sum and difference rule. So if we add two functions together and then take the integral, it's the same thing as taking the integral and then adding those together. So the integral of f of x plus g of x is the same as the integral of f of x plus the integral of g of x. And the same works for subtraction. Another property of integrals, of indefinite integrals, is the opposite of the power rule that we saw with derivatives. When we were taking the derivative of a polynomial, or x raised to some power, we multiplied the power by the coefficient, and then we decreased the exponent by 1, and this just reverses that process. So the integral of x to the n is x to the n plus 1 divided by x plus 1, and that should be n plus 1. And again, we need to be sure that we include this constant of integration. Note also that this doesn't work when n equals -1. If we wanted to integrate x to the -1 with respect to x, what we would end up getting is x to the 0 over x n plus 1 is going to be 0. So we get 1 over 0, and that's undefined. Well, it turns out that this integral is not undefined, and we'll see what we get when we integrate x to the -1 here shortly. In fact, we'll do that right now. If we remember that the derivative of the natural log is 1 over x, then we can use that idea to say that the integral of 1 over x is the natural log. Now, we do have to, for various reasons, we have to include absolute values here. There is a proof of this in the book if you are interested, but we do have to keep in mind that the domain of this function right here, 1 over x, includes negative numbers. It does not include 0, but it does include negatives, and the natural log does not include negatives. So if we were trying to take the antiderivative of 1 over x, where x is a negative number, this would be useless to us. So one thing that these absolute values do is it allows us to work with negative x values with this function 1 over x. More properties or definitions for indefinite integrals. These are the trig ones. Each one of these properties comes from a derivative formula that we've seen before. If we remember, the derivative of sine is cosine, so the integral of cosine is sine. The derivative of secant is secant times tangent, so the integral of secant times tangent is secant. Notice also that each one of these includes the plus c. These formulas also come from derivative formulas that we've seen before. Two of the more important ones are these two right here. The integral of e to the x is e to the x plus c, because the derivative of e to the x is e to the x. And then also the integral of natural log of x is x times the natural log of x minus x plus the constant of integration. This formula is not immediately obvious. For now, you can just memorize it and use it. In a future video, we will look at why that is the derivative of the natural log. If you remember, though, we did not have any functions that we took the derivative of, or any simple functions that we took the derivative of to get the natural log of x. And finally, if we wanted to verify an antiderivative, in this case we'll verify one that was not immediately obvious to us. What we can do is we can take the derivative of the antiderivative, and we should get back to what we started with, this natural log of x here. So if we take the derivative of this right here, the derivative of x times the natural log of x, we'll have to use the product rule. The derivative of x is 1, so we get natural log of x plus x times the derivative of natural log of x, which is 1 over x, and then minus the derivative of x there, which is going to be minus 1, plus the derivative of the constant here, which is 0. And so that's going to be the natural log of x plus, well, the x's cancel here, so plus 1, minus 1, and the plus 1 and minus 1 cancel out, and we get the natural log of x, which confirms that x times the natural log of x minus x is the integral, or the antiderivative, of the natural log of x. We can do this process for any antiderivative, whether it's one of the ones defined here in this video or any antiderivative that we should compute later on to confirm that we got an accurate answer.